Welcome to Lecture 4 of Introduction to Robotics. Today we're going to talk about how we can represent the orientation of an object, and specifically how we can represent an orientation change. So if you got that object in this orientation and then another orientation, how can we mathematically describe how to move from the first orientation to the second? And we'll learn today that there are many different parameterizations. In the background here is the famous Utah teapot, which we'll use to explore different ways that we can represent the same rotation. For today, you will need the online worksheet and a blank sheet of paper. Let's begin. So the background. We are given a rotation matrix named R. And we want to know what are the simpler rotations that together compose R. This is perhaps the trickiest math of the semester. I want you to approach it like this is a puzzle. And so before we get started, you must read sections 2.5 and 2.6. The content that we learned now is going to be very useful for when we solve inverse kinematics. I've given you a few links, and you'll see them in the description, of different demonstrations which I find very helpful for understanding rotation. So what we start off with here is this rotation matrix R. And what is this R rotation matrix? Well, it's a series of 9 different values. So we've got 9 numbers in here, and the question is, how many degrees of freedom do we really have in this? Is there really 9 parameters to describe a rotation? Well, that's not true. It turns out there are many constraints in here that make this into SO3. Remember, it's a special orthogonal. First off, the column vectors in SO3 are unit vectors, and secondly, the columns are mutually orthogonal. So let's write out what that means. If the column vectors are unit vectors, that means if I take any of these columns, so let's take the first column, R11 squared plus R21 squared plus R31, quantity squared, is going to equal 1. And that's also true for all the other columns. So R12 squared, R22 squared plus R23 squared is also equal to R13 squared plus R23 squared plus R33 squared. So we get 3 constraints here. And we can write them a little more concisely by just saying, well, the sum for all I of each column, so that's Rij, see that we're changing the I values in each of these. If we take those quantities squared, that is equal to 1 for j, which is in the set 1, 2, or 3. So we have 3 constraints there. The other constraint that we have is that the columns are mutually orthogonal. And so we can write that by taking any 2 columns. So I'll take 1, 1, R21, R31, take that column, take its transpose multiplied by any other column. So here's R12, R22, and R32. That quantity is equal to 0. And that's also true for the other 2 columns. And that's also true for the other 2 possible pairs. And the other pair is columns 2 and 3. Another concept that we really need to work with is how we handle inverse tangents. And so just to remind you, if I take the inverse tangent, I'm trying to discover the angle theta. So here I have this angle theta of some point that's given by this vector in xy coordinates. It's just the tan inverse of the y divided by the x. Now we need to be careful because we're dealing with this 2-dimensional quantity, and then we're taking it from yx space into a scalar value. Now this tangent function is a periodic function. It has a period pi. It can take values from 0 to pi and map onto values from negative infinity to positive infinity, but it repeats every pi units. The inverse tangent, however, maps negative infinity to positive infinity to the range from negative pi over 2 to pi. And to get the correct angle, we're going to need a little bit of work, because the inverse tangent is just taking the ratio of y and x. And it really matters for us what the magnitudes of y and x are. And so here we see the big difference between functions. One function of these is the inverse tangent, tan to the -1. And this is this blue line that has a period of pi. Overlaid on there is another function called the arctangent 2, or the 2-argument arctangent. And you can see that this function maps from -pi to pi unique values. And that's the one that we want to work with, because we want to be able to represent angles that go from 0 to 2 pi, not just from 0 to pi. So what this arctangent 2 does, you could write this yourself using just an inverse tangent function. What it does is make sure that it gives a valid value for every quadrant that you're in. And so here is an if statement breakdown for that. It would be easy to program in your language of choice. You notice it's defined everywhere except when x equals 0 and when y equals 0, because that point is right here at the origin. And if you have 0 distance away from the origin, it doesn't make sense to talk about an angle of rotation. The 2-argument arctangent function is the unique angle theta, which maps from -pi to pi. I've got a point here. I'll draw a ray to that. And so the angle that I want to know is, what is this theta? I can drop this down. This is our x value. This value over here projected is the y value. The length of this line is given by the Pythagoras theorem as the square root of x squared plus y squared. And so the cosine of theta, remember the cos is the opposite over the hypotenuse, so that is going to be x over the root of x squared plus y squared. And the sine is going to be y over the square root of x squared plus y squared. And so we want to solve what is this theta value that gives us this x and y, these sine and cosine values. I'm going to erase this. Let's do an example that compares this inverse arctangent and the 2-argument arctangent. First one, I've got xy is equal to 2, 2. So we've got 2 over here and 2 over here, which means that this distance along here is the square root of 2 root 2. For this, the inverse tangent is the inverse tangent of 1, which is equal to this angle over here is pi over 4. The arctangent 2 is going to give us exactly the same value. You could throw it into your calculator and you can see that. We get pi over 4 as well. Now let's do another point here. What happens if we put in the -2? -2. So that's this point that's way over here. And so the correct answer, 5/4 pi, or we could write that as -3/4 pi. However, when we take this inverse tangent, we're going to get inverse tangent of -2 over -2, which is going to be the same as what we had before. This will be the inverse tangent of 1. And so we're going to get exactly the same answer that we had, pi over 4. Whereas with the arctangent 2 function, the only thing that uniquely satisfies this theta with this cosine and the sine is going to be -3/4 pi. And so that's why we want this. Unless we want to restrict our robot so that it only has less than 180 degrees of travel, we're going to use the arctangent 2. And that goes for the exams as well. I want to see you using the arctangent 2. Here's a visualization of the 2 different functions. On the left is the inverse arctangent. On the left you see there's some ambiguity because we don't know whether it's going to be the positive or negative version of the angle. Whereas on the right, we will always know which direction this angle is, except at the origin. So now what I want you to do is to make yourself a paper airplane. And I really mean that. I've got myself some cougar red paper. I'm going to fold my own little airplane here. You can fold it however style you like. I've given a suggestion over here of a design that I like to make because it's reasonably easy. I want you to fold your airplane, make something beautiful. And there, I've got my airplane here. What I want you to do next is to draw some axes. And I want to have the z-axis that's moving towards the nose of the airplane, and then have the y-axis that will come up along this direction. So our x is going to stick straight upwards, and so we get a right-handed frame by curling around that. So I've drawn my z-axis and my y-axis on there. We're going to use our little plane in order to demonstrate our rotation matrix. It's always good to have something physical that you can draw on. A piece of paper is pretty safe for that, because we want to talk about revolutions around our z-axis. We might do a pitch around the y-axis, and then our x-axis is upwards, so we can do a yaw around that x-axis as well. You've now got your visual aid that we'll use today. So we're looking for a way that we can represent the frame 1 in frame 0. And the first way we're going to look at is something called the ZYZ Euler angles. And what this is a series of rotations where first we rotate around the z-axis by phi, and then the current y-axis by theta, and then the current z-axis by psi. Since these are the current, these are going to be post-multiplied. So we can write this in as a z comma phi, and then a y comma theta, and then a z comma psi. That gives us our total rotation, or we can just write it with the shorthand r z y z, with the convention that we're going to understand that these are Euler angle rotations. Then we can just write these in. And so our first one's around z, so 0, 0, 1. And then we've got our cosine, sine. Next one we have is our rotation about our y-axis, so we can write that part in easily. And remember, in this one, we've got our negative sine theta over here and our positive sine theta up here. And then we've got another rotation around the z-axis. So grab your airplane. The Euler angles is going to be a series of ZYZ rotations. So the first thing we're going to do is going to rotate around our z, which is towards our nose. So we're going to roll that a little bit by phi. Then we're going to roll around our current y. So our current y is right over here. So we can curl that up in some positive direction by theta. And then we're going to grab our current z-axis, and then we can roll around that by psi. And that gives a rotation. So again, first we roll around our current z, then around our current y, and then around our current z again. And that gives you your Euler angle rotation. And you can represent any orientation in the universe by picking numbers for the phi, theta, and psi. Now the question of the day is, if somebody gives me a ZYZ, how do we determine what these angles are? And a bigger question is, why do we even care about it? Well, we need this for the inverse kinematics. Somebody's going to tell you, I want the robot arm to be at such and such an orientation, and you've got to figure out how should we move each of the motors so that we can achieve that orientation. Now to figure out how to do that, we're going to do some math. But I'm going to do the painful math automatically here. So if we multiply out this whole thing, then we get this ugly looking rotation matrix here. And it is pretty ugly. And what we want to do is solve for that and figure out what are these angles, the phi, theta, and psi, given this big ugly matrix. To help ourselves up, instead of working with these big ugly matrix directly, we're just going to give them their row column numbers. So R11 will be this entire entry here, and then we'll be able to deal with this first. But before we go anywhere, I want to use an analogy. And this is my visual aid because solving a rotation matrix is kind of like solving a Sudoku puzzle. I don't do Sudoku puzzles, but my wife is very good on it, and I've learned the strategy. What you do is you look at this and you try to find the easiest square that exists in the Sudoku puzzle. Ones that are easy are ones that have almost everything figured out for you. Then you solve the easy one, and that allows you to solve for the next one, and you save the hardest ones for last. Because as you eliminate options, that's going to narrow the possibilities for what the answer could be. In this case, which of these squares is the easy one? Which one would be easy to start with? And this is a super easy puzzle, so it should be obvious for you. You're right. Down here in the bottom was the easiest square. It's only missing one number. And so we're going to solve for that one first and use the answers there to solve the rest of it. I've picked this Sudoku puzzle because it has 9 squares, which is kind of like the 9 entries in a rotation matrix. We're going to do the same thing for rotation matrix. So look at this big old scary entry. Which of these is the easiest entry in here? Which one is the simplest? Well, it's quite obvious that this c theta, which remember that is the cosine of theta, is the simplest entry in this whole matrix. And so any Euler angle representation that you're given, there's always going to be one entry in there that's the simplest. So R33, that's where we're going to start. Because from there, we directly know what is the cosine of theta. Now what we'd like to know is if we could use that inverse arctangent. For inverse arctangent, we need the cosine and the sine. And so now the next thing to look for is where do we see the sine of theta? And you can see, well, that we've got the sine of theta right here and here, but they're multiplied by the cosine and the sine of phi. The first thing that we're going to do is we're going to eliminate the edge case. And the edge case is that we could have a rotation matrix where R13 and R23 were both 0. The only way they could be 0 is if sine of theta is equal to 0. That would force these ones to be 0, and then your cosine would be the only one with a value in there. If they're not both 0, then that means that this cosine theta cannot be plus or minus 1. And so the cosine of theta is given by R33. The sine of theta, it's going to be hard to pull out of there, but instead of pulling it out there, we know that it's going to be just plus or minus the root of 1 minus R33 squared. And we know that because cosine squared plus sine squared equals 1. And we have two different options. Either this sine of theta is going to be positive or it's going to be negative. Those are our two options. So it's either greater than 0 or it's going to be less than 0. And those correspond with the plus or the minus that we can pick. And so we're going to get two solutions. Every solution to this Euler angle is going to have at least two solutions. And so we can pick which one to start with, but let's start with the positive value. If this is positive, then we need to figure out some entries that tell us what theta is. Remember, the arctangent 2 takes the cosine value and it takes the sine value of here. So if theta is positive, then we're just going to take that cosine is going to be R33, and then we're going to have the positive value of root of 1 minus R33 squared. Conversely, if it's negative, then we're going to have R33 and the negative value of 1 minus R33 quantity squared. So the next thing that we're going to look at is we could either solve for psi or we could solve for phi. Well, since phi's are multiplied by a positive sign here, that's going to be the easiest to pull out, because since they're both multiplied by this phi, I can just take R13, and the sign is going to be just R233. And I know that they're multiplied by the sine of theta, but since sine of theta is a positive scalar, anything along that axis is going to give us our correct angle. So we're okay here. And then we've got our phi. We've got a problem here because we've got a negative, see this negative sign over here times the sine of phi. So we've just got to take that into account. We know that we've got the negative sign times the cosine, so I need the cosine of psi here. I'm just going to take the negative of whatever value is there. So negative R31, and then our sine over here is positive, and that gives me the sine of phi, so I can just write R32. And we're done with that part. Now let's go over to the other side. We're looking for our phi. Well, we see in this column that the phi is multiplied by sine of theta, and that is negative. So we're going to take the negative value of that one. So that's R13, and this is negative R23. And then our atan 2, we know that it's negative, or it's already negative in here, so we don't have to make it negative again. That's already been done for us. So you get R31, and we get negative r32. And so again, what we've done is we looked at the simplest case, that we've got this cosine theta. As long as these two entries here were not 0, that means that this value here couldn't be plus or minus 1. Another thing you could do is you could just say, is cosine of theta, is r33 equal to plus or minus 1? In that case, something weird is happening. Now, if these two entries are 0, that means that r33 has to be plus or minus 1. If r33 is equal to plus or minus 1, that means that r31 and r32 are equal to 0, completely zeroed out. Thus, sine of theta is 0, because that's the only way that we can have those two entries be 0, because they're multiplied by a cos and a sine over there. And so what we get is a simplified like this, because we've got those zeros that sine of theta enters 4 times in this matrix. And we've got two options. Either this entry down here is positive or it's negative. If it's positive, what theta would give us a positive 1? That means that the cosine is 1, sine of theta is 0. So the only angle that can do that is theta is equal to 0. 0 radians, 0 degrees. Before we go any farther, we need to remember the sine and the cosine sum identities. Remember, if we got the sine of alpha plus or minus beta, that gives us and for the cosine, we get the cosine Next, what we can do is we can simplify this rotation matrix. We know that we've got our zeros in the bottom, and then because we've got this cosine of theta is 1, we're going to be able to cancel that out. And you notice that all these entries in here correspond to different sum identities of sine and cosine. So here's this first sign. We've got cosine theta, cosine psi, minus sine phi, sine psi. And we can see that that is just this cosine identity. So this is the cosine. Let's write it in our notation. This is phi plus psi. Over here we've got negative phi sine psi. So these are negative in everything. So that's going to be the negative of the sine there. You can see that we've got those there. It's the negative sine of phi plus psi. Right over here, it's a positive sine cosine plus cosine sine. Well, that's going to be the positive sine of phi plus psi. And then over here, we've got, if we flip that around, you see this is the cosine cosine minus the sine. And so that again is our cosine of phi plus psi. Then our entries here are 0, 0. We said this is a 1 value, it's a positive 1. What you'll notice is that they all are sums of phi plus psi. That's all we get. But we can grab it from different ways. Remember, we need the cosine and the sine. So we could either grab the first cosine, this top one here. So that's r11, and grab a sine, the one underneath it we could do, r21. Or you could say r11, and you could say I'm going to take the negative of r12. Or you could even take r22 and r21. Or r22 and negative r12. Lots of different options. They all are going to give us the same value. Now let's do the other option. If r33 is equal to negative 1, that means the cosine of theta is equal to negative 1. And sine of theta is equal to 0. And so theta, the only way to get negative is to have this be either plus or minus pi. And by a very similar argument, these are all the difference. Phi minus psi. If we want to know what that value is, we could take r11, the negative value of that, r12, negative value of that. And we could do any other combination. You could do negative r11, and you could say, oh, I'm just going to take the one underneath it, r21. Or you could do r22 and r21. Many different options for that. So you're thinking, well, what's going on? Well, it's time to grab our paper airplane again. In this case, we're saying that our theta revolution is 0 degrees. So what we have is a revolution of phi about our z-axis. We have no rotation around the theta axis. And then we have another rotation of psi about the current z-axis. And so there's been no rotation about theta. And so we cannot tell what the difference is between our first rotation, which is psi, and what our second rotation is phi. We only know the summation of those two. Similarly, if we have a rotation about our z-axis, and then we have a revolution of pi around the current y-axis. So let's do that. Now we're just facing backwards the direction we are. And then we do a positive rotation psi about that. Well, this positive rotation psi is really a negative rotation compared to a first phi. So it's psi minus phi. And then we get our net rotation there. We cannot tell how we got to that destination. But what we can do is we can come up with a number of ways to get to that destination. And for robotics, that's going to be enough to figure out how do we get our robot to a desired goal orientation.